Students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Wave Theory of Light Part 3. This is important for all the students who are giving 12 boards, IIT JEE, NEET, AIIMS and other medical and engineering examinations. Let us start the lesson. So let us start our today's video with a question. So the question is, why sky is blue, or why sky looks blue? So the answer is due to the shortest wavelength, because the shortest blue light has the shortest wavelength in the visible range. So the full answer will be the sky appears to be blue because blue light has the shortest wavelength in the visible range and hence is scattered most intensely by the molecules and atoms in the air. So let us see our next topic. So next topic, it is very simple. When a black oil spot is uh, anyhow spread in the floor, it looks very bad. But whenever the rainwater or any water smash that, then it looks very beautiful, like a rainbow color due to the reflection. Similarly, same phenomena happens, same phenomena same multicolor reflection phenomena happens on the surface of soap bubbles and DVDs. Why this is happening? So what we are doing, we are just recapping whatever we have learned in our last two videos. We have already learned that light can be studied as a wave, wave and as well as a particle. So that is the fundamental property of light, that is, it is a wave. Light is a wave, and in some situation we have to consider that all the wave properties explicitly. So for example, if or more than two light waves of same frequency overlap at a point, the total effect depends on the phase of the waves as well as their amplitudes. Optical effects that depend on the wave nature of light are grouped under the heading physical optics. So this part of optics is known as physical optics. Interference phenomena that occurs when two waves combine, and diffraction phenomena occurs when there are multiple sources of waves are present. So this is the main difference between the interference and diffraction. So example of interference is, we can see colorful screen due to the oil film or soap bubbles. This is an example of interference between the light reflected from the front and back surface of the thin film of oil or soap solution. In the previous two videos, we found that the superposition of two mechanical waves can be constructive or destructive. In constructive interference, the amplitude of the resultant wave at a given position or time is greater than either individual, either of both the individual wave. Whereas in destructive interference, the resultant amplitude is less than that of either individual wave. Light wave also interfere with each other. Fundamentally, all the interference associated with light waves arise when the electromagnetic field that constitute the individual wave combination. So let us take an example of two bulbs. If two light bulbs are placed side by side, no interference effect are observed because the light wave from one bulb are emitted independently, show that of those from the other bulb. The emissions from the two light bulbs do not maintain the constant phase relationship with each other over time. Light wave from an ordinary source such as a light bulb undergo random phase changes in time interval less than a nanosecond. Therefore, the conditions for constructive interference, destructive interference, or some intermediate state are maintained only for such short time interval, that is less than nanosecond. Because the eye cannot follow such rapid changes, no interference effect are observed. Such light sources are said to be incoherent sources. In order to absorb the in order to observe interference of light wave, the following conditions must be met. First condition is the source must be coherent. That is, so which are coherent sources? Coherent sources are those sources they who which maintain the constant phase with respect to each other. The source Next point is the source should be monochromatic, that is a single wavelength. So, as an example, single frequency sound wave emitted by two side-by-side loudspeaker driven by single amplifier can interfere, inter, interfere with each other because the two speakers are coherent. That is, they respond to the amplifier in the same way at the same time. A common method for producing two coherent light sources is to use monochromatic sources to illuminate a barrier containing two small openings, usually in the shape of slit. The light emerging from the two slits is coherent because a single source produces the original light beam and the two slit serves only to separate the original beam into two parts. Any random change in light emitted by the source occurs in both beams at the same time, and as a result, interference effect can be observed when the light from the two slits arrives at viewing screen. If the light travels only in its original direction after passing through the slits, the wave would not overlap and no interference pattern would be seen. Now it is a very important topic which we are going to start. Young's double slit experiment. So, interference in light from the two sources was first demonstrated by Thomas Young in 1801. So, in the figure you can see there are two figures A and B. A is the diagram of the apparatus which Young's double slit experiment needs to prove. So for proving the this is the apparatus where or not the apparatus, this is the semantic diagram of Young's double slit experiment, where S1 and S2 behaves as a coherent sources of light wave that produce an interference pattern on a viewing screen. So you can see this one is a viewing screen where max, min, maximum, minimum are written. And B is the diagram where the light form the light from S1 and S2 produces on the viewing screen is visible pattern of bright and dark parallel bands called fringes. Okay, So in the screen you can see the image like P, where there are dark and bright patterns. Now in the next figure you can see there are three figures. So this figure shows that some of the ways in which two waves can be combined at the screen. Figure A says that the two waves which leaves with the two slits in phase strike the screen at the center point P. So in figure A you can see the two waves coming from two slits are striking at P and bright fringe is formed at P. Because both the waves travel the same distance, they arrive at P in phase. As a result, constructive interference occurs at this location and bright fringe is observed. So now you are clear with A what is happening. Now figure V, the two waves that starts in phase but is in this case the upper wave has to travel one wavelength further than the lower wave to reach to the point Q. Because the upper wave falls behind the lower one by exactly one wavelength, they still arrive in phase at Q, and so the second bright fringe appear in this location. So in figure B you can see point Q where bright fringe is obtained. At point, so now see figure 3. At point R in figure C, however, between P and Q, the upper wave has fallen half a wavelength behind the lower wave. This means that through of lower wave overlap a crest of upper wave. This gives rise to destructive interference at point R. For this reason, a dark fringe is obtained at this location. So now we'll study about the geometrical construction described by Young's double slit experiment. That is figure A, and figure B. We have written that what we assume when we assume that R1 is parallel to R2, the path difference between the two rays is R2 minus R1 is equal to d sine theta. For this approximation to be valid, it is essential that L is greater than or far greater than D. So L should be far greater than D. So let us study about the details. So we can describe Young's experiment quantitatively with the help of the figure which we have just seen with this figure. The viewing screen is located in perpendicular distance L from the barrier containing two slits S1 and S2. These slits are separated by a distance D. The source is monochromatic. To reach any arbitrary point P in the upper half of the screen, a wave from the lower slit must travel further than a wave from the upper slit by a distance d sine theta. So you can see it here. The distance between R2 minus R1 is d sine theta. So how it has been, so in triangle S1, S2 and this triangle, you can find this value, this distance S2 to this dotted distance is R2 minus R1 and it is equal to d sine theta, normal trigonometric formula. So we can write that this is a path difference, and path difference delta is equal to R2 minus R1, which is equal to d sine theta. The value of d delta determines whether the two waves are in phase when they arrive at point P. If delta is either 0 or some integral multiple of wavelength, then the two waves are in phase at point P and constructive interference results. Therefore, the condition for bright fringe or constructive interference at point P is delta is equal to d sine theta bright, that is integral multiple of lambda, that is m lambda, where m can be 0 plus minus 1 plus minus 2 or anything. The number of the number m is called order number. For constructive interference, the order number is the same as the number of the wavelength and represented by path difference between the wave from two slit. The center bright fringe at theta is equal to 0 is called zeroth order maximum. The first minimum on either side, where m is equal to plus minus 1, is called the first order maximum, and so forth. When delta is odd of lambda by 2, the two wave arrives at point P are 180 out of the phase and give rise to destructive interference. Therefore, the condition for dark fringe or destructive interference at point P is d sine theta dark is equal to m plus half lambda, where m is equal to 0 plus minus 1 plus minus 2, etc. So you got the Young's double slit experiment thoroughly, and here we end our today's video. Hope you like this video. Please share our channel among your friends and give a like sign to this video and subscribe our channel. Thank you very much.